Hello and welcome again to Microchip's Memory Technology Series. So what's SPI? SPI is an acronym for Serial Peripheral Interface. Hardware folks will refer to the interface as SPI. Software folks will tend to say SPI. SPI was created in the mid-1980s to address the need for faster throughput speed over the existing I2C protocol. To gain that throughput speed, an additional signal was needed to isolate data to and from the host. Because of this, about twice as many logic gates are needed to implement SPI over I2C, which means that SPI devices will have a slight price premium over I2C devices. Many low-cost SPI devices offer up to 20 MHz clock frequencies, which is a 20 times improvement when compared to most I2C devices. Higher density SPI memories may even offer dual and/or quad SPI to increase the throughput speed up to 144 MHz. SPI devices are found in standalone memory devices like NOR flash, serial EEPROMs, EERAMs, and SRAM devices, secure digital memory cards, liquid crystal displays, A to D and D to A converters, and real-time clocks. This makes SPI a common and widely used serial bus across many applications, including consumer electronics, industrial equipment, automotive, and aerospace. SPI is also referred to as a 4-wire bus as there are 3 bus signals: serial clock or SCK, master out, slave in or MOSI, and master in, slave out or MISO. But because SPI does not include a slave addressing method in the protocol, a 4th signal, chip select or CS, is needed to select each slave. Here's an example of 4 devices connected to the same SPI bus. The microcontroller is the SPI bus master, and the 3 slaves are an A to D converter, a serial EEPROM, and an LCD. Note that each slave device needs its own CS signal or I/O port on the MCU. That is a total of 6 signals versus the 2 signals in a 3-slave I2C system. But remember, we gained throughput speed with SPI. SPI protocol defines 4 modes of operation related to the clock default level and which clock edges data is sampled on and driven out on. The clock default level for mode 0 and mode 1 is low, and the clock default level for mode 2 and mode 3 is high. Mode 0 and mode 3 sample data on the rising SCK edges and drive data out on the falling SCK edges, whereas for mode 1 and mode 2, data is sampled on the falling edges and driven out on the rising edges. But by far the most common SPI modes are mode 0 and mode 3 since most SPI devices honor these 2 modes. Now let's look at an SPI protocol transaction. The top 3 signals, CS, SCK, and MOSI, are all generated by the SPI bus master, and the bottom signal MISO is generated by the slave that is selected. To start an SPI transaction, the master must select the slave device by asserting CS or driving CS low. This tells the specific slave to listen for an SPI command, also called an opcode. After CS has been driven low, the master then generates clocks on SCK to shift command and/or data bytes into the slave using the MOSI signal. The number of data bytes transmitted is dependent on the transaction type and the design of the slave device being accessed. When the master requests data from the slave will transmit the requested data to the master on the MISO signal. Once the transaction is complete, the master terminates the SPI transaction by driving chip select high to deselect the slave device. Well, that is SPI. Now that you understand SPI, here's some links to other related topics that might be of interest. Thanks for watching.